Hi, I'm Sudeep Bhoja, CTO of D-Matrix. We are excited by the release of the DeepSeek R1 model and its impact on inference time compute. We will discuss the implications in more detail. So we've been following the evolution of these reasoning models, starting with the release of the O1 models from OpenAI last year. And these models rely on a technique called inference time compute, where the more computations you do during inference, the better the model's ability becomes. So this is another trend to scale AI models' performance, which we believe will unlock the golden age of inference. The this the DeepSeek R1 is among the first open source models. There's many more coming. In fact, today, Allen Institute AI2 released another model based on the 405B Llama RL model. And these models will compete with frontier models and catch up in terms of accuracy and performance to the frontier models, maybe a few months, 3 to 6 months behind the frontier models. We are excited by all of this work happening in the open source domain, where anyone can follow the algorithmic techniques used, understand the capability of the models better, and all of the open weights can be served and inspected. Now, with these larger models, we can use the R1 model, which is a 671 billion parameter model, to generate data sets, which we can then use to distill smaller models, such as Llama 8B or the Quen 1.5B and so on. And by using this data set created from the larger teacher model into a smaller student model and doing supervised fine tuning, these models become much more capable. So what this does is unlock efficiency from the model architecture and algorithmic techniques used today. One of the characteristics of inference time compute is these models are highly memory bound. And so the GPUs that were used for optimized for training don't perform as well on inference. We will get to that in a moment and discuss why that is the case. With new architectures and new ASICs purpose-built for this opportunity, we believe that efficient inference time compute on platforms like the D-Matrix Corsair will result in much faster serving speeds, much higher energy efficiency, and more cost-effective solutions. So this is some work we had done last year based on the Hugging Face 1 billion parameter model, the inference time compute of 1 billion llama, where the accuracy of a 1 billion parameters llama model on zero shot is shown below. So on Math 500, we get to about 28% accuracy. But by using repeated best of n generations on that model and scoring that with the process reward model based on a 8 billion DeepSeek model, we were able to generate performance gains, and with a couple of different techniques. One of them was a best of n technique. The other one was a weighted best of n technique. We were able to get to 50% Math 500 accuracy, which is where the zero shot performance of the 8 billion model landed. So by doing inference time compute, we got the 1 billion model to perform at the same level as the 8 billion model. So you can see that smaller models with inference time compute can perform better. Of course, there's a price to pay for that, and this is a plot of latency. With repeated generation, you incur more latency. On this was measured on a A100 NVIDIA GPU. We were measuring 18 seconds to get to the answer, and that's a significant amount of time that the user has to wait, and in all applications that may not be sufficient. So chips like the D-Matrix Corsair will be able to bring that latency down to something that is much more manageable. Since then, since the release of this Hugging Face model last week, DeepSeek, the R1 model, which is a flagship reasoning model, it was trained off a base DeepSeek V3 model with a 4-stage reinforcement learning process. In this model, there was no process reward models used. There's no search techniques like the Monte Carlo tree search used in some other applications. It was that particular model was able to perform very close to the frontier models. And in fact, the model achieved OpenAI's O1 quality on reasoning. And so with the release of the technical details in the DeepSeek technical report, as well as the open weights, the open source models have now been able to jump to the frontier. Maybe they're 3 months behind, and that's exciting for us because we are now able to see all of the algorithmic techniques such as MOE, ML, MLA, and so on that we can now dig deep and understand what exactly is going on in these models. And one of the way they do this is the base model via reinforcement learning is learning to generate the reasoning traces by encouraging it to generate this think/think tokens. So before you answer any question, generate these thinking tokens and then answer the questions. And through reinforcement learning, DeepSeek R1 learns how to keep increasing its thinking time or thinking tokens to achieve better performance. Another thing that DeepSeek did was to take that model and generate distilled versions of Llama 8B and 70B. So with the big model, you can generate these reasoning traces, and these reasoning traces, they generated, in fact, 600,000 of them, and that's very expensive if we were to do it in traditional human labeling with human labeling methods. But with these RL methods, these can now be automatically generated in domains like math, coding, science. And this data set is then used to fine tune traditional models like 8B Llama, 70B Llama, to get them to perform better at reasoning. In particular, they applied this data set to this Quen 1.5B and also the Llama 8B and the 70B models, and found that in domains like math, coding, GPQA, Diamond, and so on, that you saw significant jumps in performance. In fact, in many of these cases, the 8B and the 70B Llama models outperform the GPT-4o released in May or the Anthropic Sonnet models. In fact, it has caught up in many cases to the frontier models like the O1 Mini. So this is very exciting, and we expect that over the next 6 months, these RL techniques will be applied further to these distilled models to enhance their gains even further. Right? They're already very good, and as more R&D work happens in the open source domain, we expect these distilled models to get even better, and that's not part of the R1 release. In fact, DeepSeek calls this out in the paper that there is further opportunity to optimize these smaller models. So we'll get into some of the technical details now on the DeepSeek R1. Specifically, we will look at arithmetic intensity as a function of batch size, and this is used to figure out this is a roofline method to figure out if a model is compute bound or memory bound. So on the x-axis is a log-log plot, and the x-axis is batch size, so from 32 all the way to 1 million. and the y-axis arithmetic intensity as measured by flops divided by memory bandwidth. These DeepSeek models are a mixture of expert models. In this particular case, there's always one expert that is shared, and then 8 experts that are activated out of a total of 256 total experts. So essentially, we're activating 9 experts out of 257 total experts per token. On the average, as the batch increases to 32 and beyond, all of the experts get activated, but the compute flops decreases compared to such a dense model like the Llama 3 models, because only a fraction of the parameters, 37 billion out of 671 billion, is activated. So what you see here is, for example, on a 8K context at batch size 32, the arithmetic intensity is under 10, right? Around 4 or 5. And as the context goes up, the arithmetic intensity is still in the same ballpark, but it's closer to 10. So it's very low arithmetic intensity at batch of 32. And as you increase batch, as you would expect, the arithmetic intensity starts to increase. For example, in the 8K context length on the DeepSeek R1, the KV cache keeps growing along with batch. And eventually, as you increase the batch to 10,000 or a million, the KV cache, which is about 0.3 gig per user, is now so big that it completely eclipses the size of the 671 billion parameter model, and hence the arithmetic intensity does not increase anymore and it saturates at very high batch sizes. And of course, if the context is longer, like 128K context, you have about 4.7 gig of KV cache through the MLA techniques, and it saturates even earlier around 1,000. So that's the workload itself, and we are showing the arithmetic intensity for a 8K context and 128K context. One of the critical things is the accelerator, the GPU or d-Matrix Corsair's arithmetic intensity, and that's a ratio of the native accelerator's tops or teraflops divided by the memory bandwidth. In NVIDIA's case, that number for Hopper is about 2,000 teraflops on the compute for about 3.3 terabytes per second of HBM memory bandwidth. So that ratio is around 600, which is what you see here when plotted on the log scale. And what you see is that it never intersects the DeepSeek R1 model. So for any reasonable batch or any batch size, this model is always memory bound in token generation. And in fact, if you have a batch size of, say, 100 or less than 100, the arithmetic intensity here is so small that the NVIDIA GPUs would not be fully utilized. But d-Matrix Corsair has a much higher memory bandwidth. d-Matrix Corsair has a total peak compute throughput of 2,400 teraflops and memory bandwidth of 150 terabytes per second. So that ratio is about 16. So that's what you see here. So the accelerator enters the compute bound regime for a batch size of 32 or so on the 128K context, and then for batch size of 150 or 200 on the 8K context, right? So small batch sizes around 100 or below, our solutions already enter the compute bound regimes. See so what are the implications of this? So one of them is that models like DeepSeek R1 with chain of thought have to generate a lot more tokens compared to classical LLMs, right? They have to generate all these thinking tokens. Typically, they tend to generate 10 to 100x more tokens than classic LLMs. And for each token they generate, they have to fetch all the parameters from memory, all the KV cache from memory, and if you want to keep the user latency constant compared to classic LLMs, we need 10 to 100x memory bandwidth, right? For example, on DeepSeek, if the DeepSeek R1 generated 2K to 128K output tokens at 60 tokens per second, which is DeepSeek's claim. Most of the people serving DeepSeek today are only seeing about 25, 30. But even at 60 tokens per second, that implies about 30 seconds to 2,000 seconds of user latency per query. That's a huge, that's a big waiting time for users. Most users are not willing to wait 45 minutes for an answer, right? So it's very imperative that we bring that latency down to make these models more usable and more practical. And so our hardware, by providing 20 times the memory bandwidth of conventional solutions, for example, 150 terabytes versus 8 terabytes even on Blackwell, we can reduce that token latency by 20x, right? And the other technique in DeepSeek R1 was latent retention. With MLA, the R1 models helps compress the KV cache, right? It projects the KV cache into a low dimensional space, which would involve a 16x reduction in KV cache compared to prior techniques. And because of the use of MOE and MLA in DeepSeek R1, we see that the KV cache for a 128K context is 4.7 gig versus 34 gig with the 405B Llama 3 model, even after using GQA. So we get significant KV cache reductions, and this is good because our performance memory or any memory's capacity is always limited, so we can serve these models with fewer cards. The mixture of experts is very efficient technique in training because it reduces the amount of compute flops. One of the main reasons that DeepSeek claims they can train with far fewer GPUs than, for example, the Llama 3 from Meta. But at inference, it's not such a great thing. R1 only activates 8 experts out of 257 experts, like we spoke before. This surely reduces the compute, but it doesn't do anything for memory bandwidth, especially for batch inference, because beyond a batch size of 32, the techniques used in DeepSeek generally tends to hit all the experts. So any batched inference beyond any reasonable batches essentially activates all the experts, but then you only use a portion of the model for in the forward pass. So the active experts are 8 out of 256. 1/32 of the model is used. So as we saw in the arithmetic intensity chart, the arithmetic intensity drops of R1 drops related to dense models. We need huge batch sizes and also huge memory capacity because of those massive batch sizes to fully utilize GPU compute. And even then, it never hits the roof line. Now, D-Matrix is able to saturate at a lower batch because our memory bandwidth is much higher, and we are able to get much better utilization. Medium batch sizes of 32 to 128, more practical batch sizes, is highly memory bound on GPU. And of course, you could try to increase the memory bandwidth of the GPU. They use HBM. HBM has about 4 picojoule per bit, and if you wanted to increase the bandwidth of that by 20x, there's a huge power cost associated with that. For example, the bits have to traverse down the HBM stack across the die on the GPU. So there's a lot of sideways movement. There's a lot of up and down movement. There's a huge amount of power burned in the interconnect, driving the signals, and that will result in just for that memory interface 2.56 kilowatt of power being burnt, which is not practical. So it's very difficult for GPU compute to increase the memory bandwidth to solve these issues. Whereas D-Matrix, with our DIMC and our 3D IMC technology, we co-locate memory and compute on the same chip, right? So we can directly access all of the bits without traversing millimeters on silicon. And that helps reduce the power consumption, that makes it practical to hit the sweet spot of memory capacity and memory bandwidth for these R1 models. Finally, with distillation of 8B and 70B, and also smaller models like 1.5B and 7B, the reasoning model core is decoupled from large models that need to learn all sort of facts. Reasoning models don't need to know the capital of Nepal, for example. And that allows us reasoning models to come down in size. And with curated data sets on every domain, we feel that the smaller models will be very powerful and will start to exceed the performance on many tasks compared to traditional one-size-fits-all models like GPT-4o. And this is great for a product like Corsair because all of the parameters and the KV cache and so on fits within on-chip memories, right? And these provide orders of magnitude lower latency at much higher throughput. So we're really excited by these developments, and we expect these gains to continue. We're very excited to see all of the work going on in the open source domains, and stay tuned for more updates. Thank you.